All right, folks, welcome back. Last lecture of the semester. So today I'll probably be talking about some recent directions that I think are becoming increasingly important. I think I'll pose a lot more open questions and answers. But before that, reminder to submit your final projects by next Tuesday. Myself and the TAs will be at our office space today after class, and also Thursday during class and after class. There's no class this Thursday, but during that time period we'll be over there. So let us know if you need any feedback on your final reports, or if folks, I know some folks are submitting to NeurIPS and you want some feedback, definitely just come by and I'd be happy to give any feedback. Would also love all feedback on the course. It's the first time we're starting this course. There are a lot of great things. There's definitely rooms for improvement. So please be candid about the feedback and give us feedback through the course evaluations, or you can just tell me in person as well. Let us also know if you'd like to be a TA in the future and shape future versions of this course. I'm hoping for this to be a yearly occurrence, maybe every fall or every spring. There's definitely a lot more things that we could do. I've already gotten some feedback that, like how to make has periodic weekly assignments that are much more smaller, much more focused. How can we do the same to teach somebody about AI, having some small deliverable every week? Is that something the TAs could perhaps shape and guide the students through? So please let me know feedback on the course, and let me know if you want to be a TA and incorporate that feedback into future versions. So today's lecture, last week we talked about reasoning, specifically reinforcement learning, giving introduction to all these policy gradient optimization methods, went to PPO, DPO, GRPO, and that's been a lot of foundations for modern reasoning. And of course, most of that was in just language-only space. I'll cover some recent interesting directions in multimodal reasoning over language and more modalities. We'll use reasoning as a segue to discuss some interesting directions in AI agents, systems that use reasoning and do step-by-step actions and solve increasingly complex tasks. We talked about agents performing autonomously, interacting with the world. How do you also get them to interact with humans in the loop? So covering some new directions of human-AI interaction. And finally, I'll cover some work in understanding ethics and safety of all these modern advanced systems that we're looking at. So firstly, multimodal reasoning. I personally think the next generation of AI models will be very capable, and we have to all work towards making it more capable of doing multimodal reasoning. So what does that entail? It will be models that take in increasingly more input modalities, from language to video, audio, sensory, medical data, you name it. Learning multimodal representations from very different inputs. Talk about a lot of ways in the class, talk about different ways of fusing and combining these representations to learn multimodal representations. And then it should also be able to reason by decomposing difficult problems into multiple steps, some of which involve language step-by-step reasoning, some might involve highlighting visual evidence, auditory evidence, and maybe evidence in other modalities, and doing this over multiple times until it solves your problem. And of course, there has to be also humans inside the loop. Humans have to be able to understand every step. They might be able to intervene and ask follow-up questions. Some of these are actions that might also affect humans. But anyway, there must be humans in the loop. So I think this is a general schematic for, I don't even call this AGI, right? This is multimodal inputs, be able to break things down into multiple steps, multimodal outputs, and interaction with humans. So what do I think are the main challenges? In terms of modeling architecture, we covered, isolated topics in multimodal fusion and multimodal generation, right? Fusion is a problem of taking different data modalities and learning their correspondences and how these should be represented as features. And generation, because with multimodal inputs, we also want the model to be able to do multimodal step-by-step reasoning. So that might involve generating more text, generating more video, generating more audio. And Chanaka gave a lecture on, generative models that are increasingly being scaled to more and more modalities. So on the modeling side, as we work in multimodal fusion and generation. On the data side, we need increasingly harder challenges for reasoning, especially those involving multimodal reasoning. And ideally, these benchmarks also come with human reasoning steps. humans will break these problems down and solve them step by step. So our group builds a lot of these benchmarks and challenges. On the training side, if you have, for example, good human reasoning traces, then we've seen in class how you could do supervised fine-tuning on these reasoning steps as a good way to initialize the model to do reasoning. But of course, that is not sufficient because it's very hard to get a lot of large-scale data of human reasoning. And we saw last week in reinforcement learning how you could just train for your final objective and have the reasoning emerge, have the individual actions emerge using things like your policy gradients and your PPO methods. And finally, on the human side, of course, because we want these systems to be interacting with people, so people might give inputs, these inputs have to be a way of controlling the model, and likewise, when these models are giving outputs, they must be outputting something that is robust and trustworthy and safe if it's affecting human lives. So these are, in my opinion, the main challenges for the next couple years of AI research. So of course, in this class, as also a review of what we've seen so far, we've seen ways of using foundation models to learn these multimodal representations, transformers, large-scale pre-training, and also supervised instruction fine-tuning. So that was what we saw a lot. And then we also saw ways of how you can adapt these multimodal representations into pre-trained LLMs so that these LLMs can generate text while conditioned for understanding these multimodal representations. So that was all the work that we saw on adapting LLMs for multimodal generation. We also saw examples of enabling text and image generation. So you might want to generate some reasoning while also generating the visual explanations or highlighting parts of the image or other forms of data that a model used when making that prediction. So that's enabling text and image generation. And in terms of the part we're interacting with humans, that's what I'll be covering primarily today on some work in human AI interaction. So to first start, let me give just a shameless plug on one of our recent works that I feel embodies some of this multimodal input, reasoning, multimodal output, and interacting with humans. So this is work done by some of my students. The modalities here are vision and language, and the context is reasoning for education. So if you look at many math problems, for example, you try to solve a geometry problem, you have these shapes, and it's often useful to draw extra lines or annotations on these images to help students understand what's going on. Right? If you have this circle, for example, you might want to annotate that some lines are of the same distance, some of these are right angles, 45-degree angles. Very natural for students to kind of annotate and sketch. So the hope is that visual reasoning in both language and vision can help students understand abstract subjects like geometry. And then the goal was to use this idea to try to build some intelligent tutoring system which is able to help students learn about these abstract topics. But of course, most tutoring systems are text-based. You might prompt something like ChatGPT, and these give you mostly text-based explanations of topics. Sometimes they even just reveal the answer without even actually guiding you through the thinking process. So the goal was to kind of integrate these AI-driven multimodal interactive methods to improve learning. Not just to give the students the answer, but to help students figure the answer out by themselves. So this method that we developed is called interactive sketchpad. Interactive because it's not revealing the answer, but it's guiding the students along. And through multiple steps of interaction, the student should figure out how to solve the problem. And sketchpad describes this long history of methods which involve some common platform in which different people and intelligent systems are drawing and sketching and iterating on ideas. So we decided to call it interactive sketchpad. So as a short video demo, this is maybe some problem that a student is given. So some geometry problem, and you have to find some angles and maybe distances. And the students, maybe they don't know how to solve this problem, so they're stuck. So this is the AI chatbot that's outputting things for the students. And this is the iterative whiteboard, the interactive whiteboard that students will be playing along with these systems. So it might be stuck at the beginning. So these models will first try to think about providing some hints. It's not going to give the final answer, but it'll give some hints. For example, it might say that drawing some perpendicular lines is important, connecting some points on the circle is important, and let's visualize this using a diagram. So then it's going to start writing code, in this case, matplotlib code, which actually allows this diagram to be drawn pretty accurately because this is matplotlib code and it knows all the coordinates. So this is a diagram that is generated with some of these extra lines and annotations that is meant to help the student. And now the student takes in that feedback, the student starts drawing and figuring things out. And maybe at some point, the student gets stuck again. So then it sends this figure with the annotations, again, back to the model. And then a model would further provide some hints, for example, some theorems, some triangle properties, and those are language hints. And at some point, the student is able to use that to solve the problem. Yes, so exactly how this system worked is not particularly novel from an AI perspective, but it's about mostly putting some of these things together. So you have some problem, you first have some model to determine whether a drawing is helpful. So things like geometry, calculus, some of these integrals, physics, these are force mass diagrams. These are examples where figures are helpful. So some component figures out whether drawings are helpful. When it does figure out the drawings are helpful, it's going to generate code as a medium to generate these drawings. We iterated a couple of times between whether you should generate code and then code is executed to get the drawings, or whether you should just use a purely generative model, like a text-to-image diffusion model, to generate these drawings pixel by pixel. And of course, you get a trade-off. Code is much more restrictive, but you're guaranteed that it's going to draw things in the right place, with the right distances, the right angles. And then using a purely generative model, it's much more flexible, but you no longer have guarantees that it's going to draw the things in the right place. So in this case, we're using code, which goes into an interpreter. At the same time, you also provide textual hints. So there's hints in language and hints in vision. And together, these are visualized on this whiteboard. So you're drawing things and explaining things to students. And then a user might further annotate more of their stuff, do their workings, and that will be used as context to the next iteration of this model. Some cool results. So first, you have to check whether this model itself is able to solve these math problems. And there's been some recent interesting work on visual sketchpad, visual chain of thought. These are, again, AI-only models. There's no students involved. So it's AI-only models that's breaking things down into language and vision and claiming that helps solve difficult problems. So our method improves upon some of those, particularly because some of these previous visual chain of thought methods, a lot of things were hard-coded, and therefore ours was more general, and it was able to solve some of the limitations from hard-coding some of these visuals. And of course, the other cool thing was that we actually deployed this with students in this case study, so some of their feedback. So the graphs are a good sanity check for my workings. It was nice that it didn't give me the final answer right away, but instead gave hints and prompts to try, which is a big advantage over existing AI methods to solve the problem for you. And also other people who really enjoyed the learning experience, showing that the graphs and diagrams were super intuitive for their workings. Okay, so just as a quick case study, but I feel like a lot of future work in AI and HCI will be of this form, where there's increasingly complex ways of dealing with different modalities. There's increasingly new ways of breaking things down step by step. There's multimodal outputs in language and vision, which are very intuitive forms for human understanding. And of course, the goal here was to help students learn better. So there's going to be some humans in a loop. Another case study of things that we've been recently very interested in are these interactive agents. And these are agents that help us in our productivity, help us do things. So your task might be, for example, purchase a set of earphones with some amount of stars, some amount of ratings. And this is kind of like an offline version of Amazon. So nowadays, of course, we have increasingly powerful AI agents that are able to take in these complex instructions, break them down into step-by-step. So you first go to the search bar, you type earphone, and then you will sort by your ratings. And then you maybe sort by your previous preferences, check out, enter your shipping information, and ship it to you. And it's probably going to be a case that these agents are going to be on websites, on databases, PowerPoint, spreadsheets, phone operating systems, other database operating systems in the future, and they'll be able to automate almost any task that you give in natural language. Of course, these cannot operate purely autonomously. They should understand instructions. They should be able to figure out when they get stuck, ask for clarification questions, and humans should give feedback, intervene when these models get stuck. So of course, a loop with humans is super important. Yeah.
So I looked into this area a little bit further. So there are different levels of control, right? So the web arena or browser, or sort of the browser use, they are controlling the browsers. There's the OS level. So I think there are some companies that are trying to control the whole OS. So what do you think about the challenges or the directions of the future of the research in this area?
Great question. So I don't know what's necessarily the best platform. I think it's a lot of things that you have to balance. So web arena and video web arena stuff that we did, it was mostly about just imagining like how a human does it. Like all the access that it has is just like what humans have. So you have to tell the agent to maybe click this, or to scroll, or to type into the search bar. These are like how humans will interact with this front end website. And then yes, you're absolutely right in saying that there's other approaches which are more operating systems. So they might have access to the HTML tree or even XML in your backend, and they're not seeing things like how humans would see it, which is another way of doing it. So I think this is a general question that applies to all of AI, in fact. Do you want AI to see things and interact with things the way that humans do it? Or do they have some other way of seeing things and doing things that maybe humans don't get, but it's more intuitive for machines?
What's your answer?
I don't know. So I mean, the trade-off is, of course, if the model is doing something that is more intuitive for machines, it could be faster, it could be more efficient, but it's less interpretable to people, right? But then in this case, this was the agent, and it is kind of like moving the cursor, it is scrolling, and it's doing things that humans are. It might be more understandable to people. So there's a trade-off, but of course, it might not be as natural for the AI system. Another actually good question here is that I'm recently involved in some grants on detecting the difference between human behavior and AI behavior. Because we know that AI agents are going to be increasingly present on like all your database and websites, right? So people, I'm sure, companies who want to build agents, which want to integrate advertising into agents, they're going to try to make the agents mimic human behaviors. So that might entail scrolling slower than how fast AI agents can actually scroll, or taking more time to type than how AI agents can actually type. So there's kind of adversarial detecting AI agents and also trying to make AI agents undetectable, like making them perform similarly to humans. Yeah.
And there's also a bunch of research happening with people trying to figure out how to trick these agents into buying things.
Yes.
Simply by listing things or phrasing things in a particular manner.
Yes.
I don't know. So there's also, if they were just using an API call, maybe it's harder to trick an agent into buying a certain product. But if we put them out on these human platforms, then maybe, there's more noise, and so they're maybe easier to manipulate. So that's a big problem.
Interesting. I mean, that's a very cool result. Although I don't agree that if they only have access to the backend or HTML or API, it's going to be harder to trick, because there's probably equally easy ways of injecting adversarial attacks in that medium as compared to the visual medium. Yeah.
Just a quick comment. So the brand you mentioned is super interesting, because basically you can create a reCAPTCHA for, right? Because reCAPTCHA is for humans to detect human behaviors. But now AI can mimic human behaviors, then it's going to be hard to detect the bots. Yeah, super cool.
Well, I mean, that's the question actually. I feel like reCAPTCHA should be trivial for AI systems. Do people not think so? Based on just like detecting like motorcycles and like buses, this should be trivial for AI. I feel like modern AI can definitely solve it, but why do CAPTCHA still exist? Do people know?
So the response time, right? So human takes longer time and more errors to get it right, and AI just.
So AI is better, but now CAPTCHAs are just checking whether
it's human.
The pattern of movement of the mouse or the time is the same.
Yeah.
I feel like AI should be able to mimic that very easily nowadays as well.
Yeah, that's what we need reCAPTCHA for. What's in that? That.
Okay. Interesting stuff. Interesting, lots of ethical concerns. Okay, so of course, it's not going to be trivial to get all these agents scaled everywhere. So here are some of the main challenges and directions I think are most important. So one, of course, is reasoning. Leveraging, for example, some of the ideas that we saw in last week on using RL, breaking difficult problems down into step-by-step parts is going to be very important. One thing that we've also found very important is to disentangle what we call high-level reasoning versus your low-level actions. So high-level reasoning might be, go to the search bar and click and search for something. So it's high-level natural language, but in fact, this high-level reasoning actually involves multiple low-level actions, right? And actually moving the cursor to the search bar and typing these characters and then typing enter. So first, how do you take in these difficult problems, break down the objective into high-level plans, combine a high-level plan with what is observed in the visual web page, which might be the form of image, visual image, or it could be your HTML, and then generate possibly multiple low-level actions. And these low-level actions are the level of type a character or click on a button or hover around or scroll somewhere and keep repeating until you solve the task. And this idea of breaking things down into like high-level reasoning plans and low-level actions, again, not new. It's a big thing in robotics. A lot of work integrating LLMs in robotics, also high-level goals, and then you actually break the high-level goals to individual, for example, robot actions. That's going to be very important. Yeah.
For the sketch paper you just shared, right? So AI basically run the code and generate the static image, and then it's humans analyzing those images. So also you did a web arena. So have you thought about combining those two, right? Maybe give let AI control the browser and then draw on Sketchpad, right? Along the users.
Interesting. Yes. So maybe it could be a cooperative thing, right? I mean, nowadays these models are already getting very cooperative. Like some of these startups, I think the main pitch is that these models would live on the phone, and then you could of course do your clicking as you want, but then at any time you could delegate to some assistant or agent. But I think it'd be great if these agents could kind of show us what they're doing, right? It's going to show us their thinking process, show us where they're looking at, show us what their decisions are, show us what kind of current reward functions are. So this cooperation is going to be important. Yeah, but yes, great question. So one big direction is first breaking difficult problems down into high-level planning and reasoning, and then also breaking down high-level reasoning from low-level actions, which multiple low-level actions might be executed for each high-level reason. So here's an example. This was some of our experiments. You might want to buy the highest rated product from this NS Switch pouch, like Nintendo Switch pouch category within a budget under 60. So you could imagine directly searching and entering a price, but the model gets confused and it's not able to deal with both the item and the price at the same time. Whereas sub-goals would first search for this pouch. So it just does one thing, it searches for the pouch and just types one thing. And then it would go in and further, maybe put a price range from $0 to $60. So at least this very simple case, just breaking things down into two steps, help the model substantially instead of having the model try to figure out everything immediately.
So those are the two steps of the low-level actions?
Well, these are the high-level actions. So search for these are high-level actions, but the specific low-level action is that you first have to navigate to the search bar, you have to click on it, and then you have to type.
So the ones that we're controlling is only the high-level instruction.
Well, both are LLMs.
Okay.
It's just how you can orchestrate these LLMs. So you first orchestrate LLM to break down the task into some high-level actions, and then you would ask the model to kind of break down these high-level actions into more low-level actions, right? Given that the low-level actions can only be maybe one click or one type or one hover or one scrolling action. So there's much more. So you can think about this as natural language, and this has to be just like 5 most basic web actions that you can do on your computer. Breaking these things down, breaking these difficult tasks down into step-by-step also helps humans intervene. So human in the loop. So here's one example. So here, this task is a bit harder. Is what is the price range of wireless earphones in this one-stop market? So again, this is not something that you can directly search for. You got to do quite a few things, right? You got to search for it. You got to sort by the lowest price, sort by the highest price, find the range, and then return the answer. So if you just ask the model to plan, it would first do the searching, which is correct, and then it would try to find the price range. But of course, this price range isn't directly annotated on the website, so the model gets stuck. And then you give it some examples, it does a little bit better. So it searches for the wireless earphones, it finds the price of the first earphone, but it's really assuming that it's sorted, which may not be the case. So even if you give more examples of how the model should plan, it doesn't get much better. So one thing you can do then is to get humans to interject. So we call this few-shot high-level planning with human clarification. They might search, search was correct. And then once it searches, the model basically signals that it doesn't know how to proceed. And again, that in itself is an open question. How do you get models to signal to people when they are confused? But one way of doing it is, when the model is generating action, you let it repeatedly generate the same action like 5 times, right? If it generates always the same next action, then it's very confident. If it generates 5 actions that are very different, then it's not confident. And therefore in some sense, you can say it's kind of confused. So that's kind of like uncertainty, the method of using uncertainty to measure how confident the model is. Yeah.
So 5 times same action, have you explored using one step, but with the confidence score? How accurate is the confidence score driven by the LM?
What the issue there is that most APIs don't have confidence score.
Or we just ask LM to generate confidence scores and so on.
Just prompt to generate confidence score.
Yeah.
We never tried that. It could be interesting to see.
Doing that right now, politics. And then I was curious, like, also, I know there's like research about like doing self-consistency.
Right.
So, is there a general like method to check that? Like, do you just prompt it like 5 times and then output? Maybe do it the other ones.
Yeah, there's a whole field of machine learning, which is called uncertainty quantification, which basically says to what extent can you resample from a model k times and have that k different outputs be a good measurement of the actual distribution of the model. And then if models are reasonably calibrated, which nowadays these models are to some extent, then they actually are pretty reflective of whether it's like a very sharp k samples or very evenly distributed k samples, and that's a proxy for uncertainty. So but yes, the big assumption is how calibrated, how consistent these models are, and if people are looking at how to improve that consistency.
You're saying it didn't sort multiple times, and like none of them sorted, or like how would you define?
Yeah, so for these, it just would never really get it correct. Of course, no, there is the off chance that you would get it correct, but you cannot rely on that off chance. So we basically found, models are pretty consistently, when they get things wrong, they are unconfident, which means that you sample a few more times, they can do something again quite different, which is good, which means that you can use the sampling strategy as a way of calibrating or telling you how good your model is calibrated or how confident your model is. So in this case, at some point, it had really high entropy. It was confused, and what you would do is these are ground truth plans that are human annotated. So humans would just write these were the things that they did. So the model is stuck. Just imagine the human give the next step to the model, right? Maybe so in this case, the human gives the next step, which is you should sort the prices from low to high, right? And just interject that and tell the model this is the next right plan to do. And then a model would be able to continue after this correction without having to refer back to any humans. So we then find the lowest priced earphone, which is the first entry, because you sorted from low to high. Then you will resort from high to low, and then you will find the first entry once it's been resorted from high to low. So in this case, just given one piece of human planning, one piece of human help, human demonstration, and it can start solving the rest of the plans more accurately, which is pretty good. Yeah.
Are all the plans very generated before they execute each individual plan, or each individual step, or it's like off a go, right? We do one step and then we figure out the next step after I execute the current step.
It's autoregressive, right? So it's generating this plan, it's taking those actions, and then it generates the next plan with those actions.
Okay.
Yeah.
So one step at a time.
Yeah.
Okay. Why not just all the steps ahead of time?
What was that?
So generate all the steps ahead of time, right? So I'm going to search first, and then I'm going to sort, find, and find. I'm going to finish all the plans first, and then execute on them one by one.
Oh, no, I'm confused. So yes, it is taking this, it's generating all the plans first, and then it's executing each one at a time. It's executing in terms of low-level actions, each one at a time. And these human ones were just, and these are just like small case studies. So we don't have like big tables of results, but these are also humans just annotating like maybe 10, 20 examples. And then we try to give 1 or 2 or 3 human interventions and see how much the performance starts improving.
Oh,
Yeah.
in terms of how the humans like injected in the planning phase or in the action phase, like you suggest.
In the planning phase.
In the planning. So when the model generates the first search, and then you give the model next step, and then it based on what you give and what's the first you generate the rest.
Right. So with this generation process is autoregressive. It is going to be take one after the other. In this case, it generates 1. We see this high uncertainty. You kind of just copy this over and tell the model this the second plan is just given is correct, and then you just see whether you can generate 3, 4, and 5 correctly.
And which step will you like give the parameters to model is when random choices or?
So in this case, it was by this uncertainty measure, right? So you're prompting the models, and then every time you prompt like k times, and then you see what is the distribution over the k next plans that it generates, whether the next k are exactly the same, in which case you can confidently say, yes, the model is just always going to do that, and it's a good thing. But then at some point, it's going to generate k, and their k are going to be very different. And when it's very different, we're using that as a proxy for the model being uncertain about what next to do.
Oh, when the model feels like
Yeah.
confused or something like that.
Right.
With the development with the parameters.
Yeah. Talking about the AlphaGo, of course, I think another big direction is interactive agents with search. Right, everything we've been looking at so far, these are at the planning level. So planning with humans in the loop, planning with step by step. Now low-level actions is just not easy to deal with. You can have like perfect plans, right? I feel like planning is probably the easier part, but then how do you convert these plans to individual low-level actions? Right? And low-level actions are again these like individual clicks and scrolling and typing. And it generalizes to other problems as well. So one thing we are also interested in, and I think the community is broadly interested in, is how to integrate search as a tool in these like large models today. So in this case, for example, you might have a question: how many times did I purchase this product? And then again, it's quite a difficult problem. So you have to go into like my account. You have to click on several things like my orders, my downloadable products, and there's all possible things that you can click on. And you can go to my orders, and you might have a ton of orders, right? Maybe you have to open up each order and check which ones are similar to the current product or different. And maybe these products' names evolve over time, so you still have to kind of keep track of that. So this is a very difficult search problem. You cannot, of course, search through everything. So one thing that is quite interesting is searching, but also pruning where you shouldn't search. And how do you prune? Well, last week in RL, we talked about this value function, right? Value function, essentially, you can view this as a big tree. Each of these are states. So the current problem, the current web page that you see, and the current links to and from the web page. And then you can try to estimate what is the value, how valuable that state is. Should I be in that state when I'm trying to solve that problem? So if you're at a page where everything is blank, you've not purchased anything, then that's probably a bad state to be in. If you go somewhere where there's a HTML error or there's not much information, that's probably a bad state to be in. And then if you're in some of these order pages, because these products maybe match the task, it might be good states to be in. So how do you do this search recursively while pruning branches that may not be useful so that you can stay efficient? It's a big problem. Yeah, and ways of integrating reinforcement learning, integrating tree search with LLMs, also a big direction. Great. And of course, from these virtual digital agents to also embodied agents, there's a growing community of people who are building what we call these vision language action models, so VLA, or maybe video language action. So these are models that take in vision, so the robot, or in this case, the simulated robots are seeing something, it's taking in language instructions, and it's generating actions. So ways of controlling these robots and taking actions to solve these tasks. Yeah, so language part is Llama 2, vision part is vision transformer. Again, this is the adapter that we saw. And as a prefix, it's adapter, it's a prompt, and it's decoding actions. In this case, changes in your positions and angular velocities and grips of this like robot head. Yeah. Another cool stuff. Lots of big applications in these robotics and body agents. Great. Any final questions on agents, robotics, interaction? Yeah.
Just a comment on the purchasing agent. I mean, it seems like it would be an environment that's very easy to just kind of fully automate, like in a reinforcement learning manner. Is that how they're trained? Because I feel like that it's kind of like a playground, right? With this type of environment. So I feel like that I don't know if you could even overcome the whole planning step procedure of it, but I don't know. Is that worth doing that?
Yeah, I think again, two broad strategies. Like some people believe in kind of the model exploring and searching and doing RL. Some people believe in using as much, language knowledge to break things down procedurally, and then maybe using RL just for fine-tuning. So I don't think there's a consensus. I would say these purchasing platforms are not as small as some of these games, like for Pong and Atari, where these RL things first started. Yes, the action space is actually very small. And then the state space is also quite small. But in these purchasing things, they can quickly get very big with amount of images and number of links and the complexity of the potential actions. So I don't think you could be able to do pure RL from scratch. It probably is going to be very good initialized vision language models, planning, and then maybe you do RL for fine-tuning some of the local actions. And purchasing is also just like one of the maybe smaller applications, right? I mean, the bigger ones are, coding or resolving GitHub issues or manipulating entire databases. So again, RL might not be too feasible with the size of the state and action spaces. Yes.
In this paper, you talk about controlling different robots with the same model, about the specific training on new models, but always the same number of degrees of freedom, same like attention mechanism and effector, right? It's not actually important to a different number of degrees of freedom and a different kind of effector.
Yeah. Yeah, it's still the same kind of like gripper robot. But I wouldn't see any reason why with future scale, it wouldn't generalize across robotic form factors.
There's an interesting paper, Nomad or something, where they do kinematics agnostic models. So
yeah,
they used to drive like the spot robots, drones, and things like that. I mean, I wonder how it can be applied to this kind of where we change the number of degrees of freedom.
Yeah, that'll be a good question to study. I mean, you're asking two questions here. One is, how much do you integrate kinematics? I'm sure you're saying that model has maybe a kinematics model, and this has no kinematics, right? This is just purely from language. So of course, studying the hybrid would be very interesting. And then of course, separately studying whether these actions could generalize. I mean, multitask learning has existed for a while, and you could very conceivably think that just like there's input adapters, so adapting to different input scenarios, and the only thing that you have to train is this small thing over here. There could be also output adapters, right? And each task head might be different. And I think people are already doing that. So I think future is, of course, big general knowledge, but input should be very modular, and output could be also very modular. Reasoning should also be very modular. Yeah.
So I know that the O3 was recently released by OpenAI, and one of the things that they did was train it on a lot of tool use. So, I mean, not agentic in the sense that it was interacting with an environment. But I'm just kind of curious in terms of like, if will be part of this lecture that is going into that like tool use, or like, what's your opinion on the?
Yeah, I didn't prepare. anything on tool use, I mean, I'm a big fan of it. I think, again, it really fits in this paradigm, right? So yeah, you have big base model.
Yeah.
And it's really about making the input super modular and the output super modular. So tools are exactly a good way of doing it. I also view like tools as a different modality that you might want to align the capabilities of the tools with the language model. I think the biggest question is what is the bottleneck? So right now everything is kind of going through language. Whether it's tools, you're describing how to use tools and calling those APIs using language or code. Vision is kind of being adapted into language. Outputs, these robots are being parameterized as language angles and rotations. So is language the right bottleneck? Right now, that's what we have as the best base model. So perhaps it's fine. Of course, with more progress in multimodal LLMs, you may not need a language-only bottleneck. You can maybe really just have things that are being done visually.
Right, Meta did a large concept model recently, which again was based upon a large language model and trying to model concepts within the neurons of the model. But
right,
yeah,
right.
Interesting.
Yeah, and tools, tool use is very interesting. And of course, people are integrating tools with all these agents, right? So tools with you need a calculator agent if you want to do, your spreadsheets. You might have a web browsing agent. You might have other agents that are very commonly used in these other tools, very commonly used in agents. Yeah.
Because I'm also interested in the tools I think it's general of the what tool is going to use and what is going to be used. And also you mentioned like getting like different models kind of assembled together to do the base model of different languages.
Right.
If there were a multimodal base model or multimodal foundation models, for the output, how will the output like change? For example, because like right now those actions or like different tools is still like processing faster. I can see how the multimodal will improve the input side, like you can directly process the images or using this.
Right.
How's the output like in these agentic actions? Like
so how
I think the actions is better described in language, but
so that's a fair point. So first, well, two things. First of all, multimodal LLMs are better than LLMs that just reasoning about the world. If there is some like visual phenomena or there's some physical phenomena, especially important for robots, just replacing this with increasingly better vision language or audio language models will become increasingly better at representing the world. So then of course your tool use could also be much better. Then your other point is about how do when these models interface with tools, is it always just going to be language? It's a fair point. I think code is, and maybe language and code are the two biggest ways of interfacing with some of these tools nowadays. But I mean, one other example of a tool that, there's also like visual tools, right? Like OpenAI's O4 has this cool thing where you can like zoom in, zoom out, and you can crop things, crop different patches. So it's very much a tool that is, of course, going to be instructed by language, but it's very much requires visual understanding. And in the future, some of these tools, like for example, speech recognition or text to speech, all those could also involve. Again, the orchestrating modality could very well be language, but it has to have the understanding somewhere in the model.
Okay, so sorry, I know we're asking about, but I think one thing that's very interesting too, it's just fun because the OpenAI models is like the way you get exposed to these concepts beyond the papers, and it's fun. Like started trying it recently, and one thing that these systems do is that they use the tools also as a sort of like environment where things can be evaluated, which is very useful for training, right? That the tools can be, you can have this kind of reinforcement learning situation come out of the tool use. But there was a coding problem, and it ended up using an IDE in order to recreate the code that I thought that I had, and then it looked into the packages that was in this coding IDE in order to debug. So it would do the debugging itself instead of interacting with me and letting me do the debugging on my end. And I thought it was so weird to have it sort of like interact with this IDE like the way that you describe it here and just like go into the packages that were loaded into the environment and so forth.
Yeah.
It seems like a very promising area going forward to have this kind of these environments that are interacted with through tools in some simulator environment in order to optimize like how to model things and debugs.
Yes, yes. Well, I mean, but also it's probably a case that these models were trained already in that environment, right? But we're gonna probably like fine-tune some of those models in these debugging environments. That's why it has this capability. And I would say probably a lot of the models that in the future would be, trained on like websites and web navigation already before release to the public, right?
Right, but it's just kind of interesting this whole way that it helps you is it does all the work without including the human. It's like just trying to help you do something in your browser. It's like, oh, let me just like do it in my own browser first and then debug the entire thing and then get back to you once I run all the simulations.
Yeah.
It's interesting.
I mean, good segue to this very last part, which I'll cover some of my thoughts on human AI interaction. Of course, you're alluding to this. Big topic. A lot of people approach it from different perspectives. Here's what I think. So 3 big questions we need to answer. Of course, I'm very interested in what mediums are the most intuitive for human AI interaction, especially beyond language prompting, whether that's a more code-based or visual-based or even physiological-based ways of maintaining the fidelity that you get with language, but significantly reducing, for example, cognitive overhead or burden would be very interesting. And of course, all this about building, from a technical perspective, all this about building, multimodal interfaces for human AI interaction and exploring the switching between and fusion of different mediums. Another, big set of questions I have is, what new technical challenges in AI have to be solved to enable human AI interaction? So from the AI perspective, AI researcher, personally as AI researcher, what new AI problems have to be solved? And I would say a big one is quantification. And I'll get to quantification in a second. I'll give a formal definition, but at a high level, it's really about providing better understanding and control over these models. And of course, you have these more human-centric questions, like what new opportunities arise from integrating AI with human experience, how they can help productivity, creativity, well-being. And these are good patient-centric questions. But my main concern with some of these is that it's just very vague, not very well technically defined. The application-wise is very interesting. So, I mean, 1, we talked about a lot in the class. Let me jump in on 2 and gives us some final thoughts in 10 minutes. And 3 of it are mostly applications. I think everyone has their thoughts on how AI could be integrated to help people. But quantification is probably the most important thing that we've not talked about in the class so far. And that's because most of the class has been focused on building new algorithms, new techniques, applying them different things. Quantification can be formally defined as empirical and theoretical study to better understand model shortcomings and predict and control model behavior, right? So it's not too much about building new models in itself, but building new understanding and science and techniques and theories to understand and control model behavior. So 3 things I highlighted. 1 is shortcomings. When do models fail and why do they fail? Can you predict when they fail? Model behavior, some of it is about interpreting the internal behavior, but also understanding their behavior as a whole on different types of inputs. And also learning how can you predictably understand how models learn and get final performance and how they scale with more parameters. And again, here's just a quick crash course over several big advances in this space. I mean, everyone has seen safety, right? LLMs are very easy to capture biases. We did a lot of early work in this, where gender bias would affect how language models complete their outputs based on different occupations and how they describe different ways that people perform these occupations. Of course, this is all old news now. Everyone knows that there's language, gender, racial bias, all that in LLMs. Not going to cover it too much. A lot of ways in kind of improving the safety, but impossibly number of ways to jailbreak. We can never, I don't think there's ever going to be a way of not having models susceptible to jailbreaks. This is a paper I love very much. You prompt how to build a bomb in language. Models nowadays say, sorry, I can't do that. And then you just prompt it in ASCII. ASCII how to build a bomb. And the model would say something, give you the right answer. So increasingly, this infinite space of jailbreaks. I don't think you can ever rely on models being safe 100% of the time. So still a big challenge. Also interesting to me is also when you start building these like multimodal LLMs, is it easier to make the models safe, or do these models become even more unsafe? So of course, most of the times they become more unsafe with more inputs and more understanding. There's more likely chance of capturing biases. So a lot of these models, when they started, they kind of just only looked at the image and only looked at the question and ignored the image, because 90% of bananas are yellow. They don't actually predict green bananas. So lots of ways of kind of rebalancing your data and rebalancing your training so that models are actually learning from different modalities equally. Social biases, so people who started looking at these image captioning, they were very confused why they kind of got the description of the people incorrect. For example, there's a man sitting at a desk with a laptop computer. And then the people soon realized that oftentimes the model just looks at some object in the image, for example, detects a laptop, and then just infers, for example, the type of demographic of the people who be using computers. And oftentimes that would reflect biases. Here's another example. This was studying vision language models, and their basic conclusion is that there's worst of both worlds. Your biases compound when you start putting vision models with language models together. So they tested, for example, models like Theo Bert, and they gave it different pictures of different people holding different things, and how would they be what their demographics and race and gender was. And they basically found like models became more confident at reinforcing biases when they saw both image and language, which is not good, of course. Let me skip over some parts. So another big area is robustness, right? We've seen a lot of cases where models just perform well on the settings that they were trained for, but they don't become robust in the real world when they see different types of noise in your sensors, in your images, in your text, different types of noise in videos, for example. And here we did a very large scale study about 2 years ago where we saw performance of different large models and their robustness. So how much their performance dropped when you introduced different types of noise. And we basically found a negative correlation, roughly, where models that perform really good were also not really robust. So they could see much worse performance drops despite starting off as higher accuracy. And lots of ways of dealing with this noise dropout, or introducing what you expect the model to be sensitive to during training is a way of doing it. Also translating from one to the other to try to infer missing modalities is an interesting way. Okay, I think we are out of time and the next folks have to come in. But I also have some slides prepared. I'll put all these slides online about understanding model behavior. So there are increasingly better ways of doing interpretability, visualizing neurons, visualizing gradients with respect to the input, so highlighting parts in the text and the vision, which are responsible for dealing with different predictions. And one thing I also want to highlight is how to evaluate quantification, right? Quantification is a big topic. It's about coming up with understandings of these models. But while accuracy is easy to measure, if you're building a better model, it's more accurate, you're happy, how do you measure the success of some property that you're trying to study in this model? Because ideally, no one has studied this property before. So there is no ground truth, which you can say, I'm understanding this property 80% correct. So evaluating quantification is still a very big challenge. One of the things that we've been proposing are indirect ways of evaluating quantification. So if you, for example, if you claim to highlight a certain property in the model, for example, the model focuses on color more than this other color, can you simulate the model? Which basically means if I give you a new data point and I give you the model, can a human simulate what the model would predict? Both in the case when the model gets it correct and the case when the model gets it incorrect. So having people simulate these models. So if you have purely black box models, then humans cannot simulate it. But if your models are more understandable, then humans should be able to simulate it. Another cool thing we've been doing is using humans to debug these models. Again, if I have some quality, some magnifying glass, and some property of these models that I'm claiming makes sense, then humans should be able to look at these and ideally find different bugs in a model and improve the performance of these models. So that's again some directly measurable quantity, right? If there is a bug that you found and performance improves, then that means your understanding is correct. Okay, I'll put some more examples online, but yes, we have to go. Thanks everyone for a great semester. It's been a pleasure teaching this class. Please get your final projects in and please leave us feedback for the course and fill out those course evaluations. And please let me know if you want to be a TA and shape future versions of this class. All right, thanks everyone.